We've talked about software supply chain attacks and MSP compromises. So let's look more into the subject of open source software and dependency chain attacks. Modern software development relies heavily on open source libraries and frameworks, as we mentioned in the first lesson of this section on supply chain attacks. A typical application might include hundreds or even thousands of dependencies, open source components that developers didn't write themselves. Those dependencies create a complex web of trust relationships that attackers can exploit to reach millions of downstream victims. Modern software development has shifted dramatically toward component reuse. Let's not reinvent the wheel every time, right? Let's use what's already written and build on that. Developers use open source libraries to provide common functionality. This approach makes development faster and leverages community expertise, but it creates complex dependency relationships. Your application depends on libraries, which depend on other libraries, which depend on still other libraries. These transitive dependencies create change that extend many layers deep. It could go down as much as 50 layers or any number of layers. Under the hood, you have no idea what really is there as a general user. Using open source dependencies requires trusting their developers, maintainers, and the ecosystem infrastructure. Developers assume that popular open source packages are safe because many people use them and someone would notice malicious code. They assume maintainers are trustworthy because they've contributed to the community. They assume package repositories screen uploads for malicious content. These assumptions are often, but not always, justified. Many open source developers are genuinely trying to create useful tools, but attackers understand these trust assumptions and exploit them. So attackers compromise open source ecosystems through several distinct methods: compromising maintainer accounts, to push malicious updates to legitimate packages; typo squatting by creating packages with names similar to popular packages, hoping developers will mistype; dependency confusion by uploading public packages that conflict with private internal packages; submitting malicious contributions to projects, either directly or by becoming trusted contributors over time; compromising package repository infrastructure itself, creating seemingly useful packages that contain hidden malicious functionality. Each method exploits different aspects of how open source development and distribution works. Open source package maintainers are high-value targets because they control what code gets published. Typo squatting exploits the fact that developers sometimes mistype package names when installing dependencies. An attacker might register a package with a name like REQEUSTS instead of REQUESTS. When developers mistype the package name in their installation command, instead of getting an error, they just automatically inadvertently install the attacker's malicious package. Some typo squatting packages have been downloaded thousands of times before being detected and removed. Dependency confusion attacks exploit how package managers resolve dependencies when both public and private packages exist. If a developer specifies a dependency name without explicitly indicating it's from a private repository, the package manager might retrieve a public package with the same name instead of the intended private one. It creates an opportunity for an attack that requires no credential theft or account compromise, just simply understanding naming patterns and package manager behavior. Attackers sometimes contribute to open source projects with the goal of eventually injecting malicious code. Open source projects depend on community contributions, but must balance welcoming contributors with carefully reviewing all code changes, a balance that attackers exploit. There's a relevant insight from the philosopher and mathematician Alfred North Whitehead. In his book, An Introduction to Mathematics, he wrote, "Civilization advances by extending the number of important operations which we can perform without thinking about them." Whitehead was describing how progress often involves automating or abstracting away complexity so people can focus on higher level problems. This principle applies directly to software development and dependencies. Progress in software development has come partly through creating libraries and frameworks that handle common operations, so developers can focus on application-specific logic rather than re-implementing basic functionality. But this advancement creates vulnerability. When developers use dependencies without thinking about them, without understanding what they do, how they work, or where they come from, they inherit all of the security implications of those dependencies without conscious evaluation. The efficiency that comes from not thinking about dependencies also means not thinking about their security, provenance, or trustworthiness. The same abstraction that enables progress also enables supply chain attacks. Transitive dependencies, dependencies of dependencies, create particularly difficult security challenges. Most developers don't even know what all their transitive dependencies are. Build tools and package managers handle dependency resolution automatically, and developers rarely examine the complete dependency tree. Modern applications often have hundreds or thousands of dependencies, creating management challenges. Each dependency is a potential security vulnerability. Each represents trust in external developers. This dependency sprawl creates systemic risk that's difficult to manage even with significant resources and expertise. Package repositories like NPM, PyPy, RubyGems, and Maven Central are central infrastructure for open source ecosystems. These repositories host hundreds or thousands of packages used by millions of developers. They're critical infrastructure, but often run by small teams with limited resources. The balance between welcoming community contributions and maintaining security is difficult. Overly restrictive policies would harm the open source ecosystem. Insufficient restrictions enable attacks. The LeftPad incident in 2016 illustrated how fragile open source ecosystems can be. LeftPad was a tiny NPM package, just 11 lines of code that did something trivial, but thousands of projects depended on it, including major frameworks and applications. When the maintainer removed the package from NPM, it broke builds for thousands of projects worldwide. The incident was not a security attack, but it demonstrated how small dependencies create systemic risk. If removing a trivial 11-line package can break large portions of the ecosystem, imagine the impact of compromising widely used packages with malicious code. And of course, detecting malicious code in dependencies is extremely difficult. Manual code review doesn't scale to hundreds of dependencies. Even skilled security reviewers struggle to identify well-hidden, malicious functionality in unfamiliar code bases. Many compromises are unable to be discovered through routine security practices. Developers face difficult trade-offs with dependency updates. Version pinning, specifying exact version of dependencies rather than accepting automatic updates, provides stability and prevents unexpected changes, but it also means missing security updates that fix vulnerabilities. Automatically accepting updates ensures you get security fixes, but might introduce new vulnerabilities if an update is compromised. It also risks breaking compatibility when updates change behavior. Many developers pin versions so things don't break, but don't regularly review and update them, resulting in applications running outdated dependencies with known vulnerabilities. Every approach involves accepting some risk. Many critical open source projects are maintained by volunteers who receive little or no compensation. They're not paid. These maintainers create valuable software used by millions, but often work alone or with small teams. They face increasing demands, feature requests, bug reports, security issues, without corresponding increases in support or compensation. So there's what's called maintainer burnout, which leads to packages becoming unmaintained or poorly maintained. There's nothing forcing them to keep maintaining them. If they're bored or tired, or they simply don't have time, then it's done. Security issues might not get promptly addressed. Updates might become infrequent or stop. Code review might become less thorough. This creates security implications throughout the ecosystem. Critical infrastructure that depends on volunteer maintenance faces sustainability and security risks. Various tools attempt to address open source supply chain security. SCA, Software Composition Analyses tools, scan code bases to identify dependencies and known vulnerabilities. They generate dependency inventories and alert on security issues. Dependency monitoring services track dependencies and notify developers about updates, vulnerabilities, or suspicious changes. Package signing and verification mechanisms attempt to ensure packages haven't been tampered with. But these tools have limitations. They identify known vulnerabilities but struggle with novel attacks. They generate many alerts that developers must prioritize and address. They cannot verify that code is safe, only that it matches what the maintainer published. And software bills of materials controls. SBOMs provide visibility into what dependencies are present. An SBOM lists all components in a software application, including versions, origins, and relationships. This allows organizations to know what they're using, identify when dependencies have issues, and respond when vulnerabilities are discovered. Regulatory requirements increasingly mandate SBOMs, particularly for software sold to government. This practice is spreading more broadly. But SBOMs are only helpful if they are accurate, complete, and kept updated, which requires tooling and processes that many organizations don't have. A fundamental challenge is that truly verifying open source dependency security is effectively impossible at scale. You could theoretically review all source code of all dependencies and transitive dependencies, but for applications with hundreds of dependencies totaling millions of lines of code, that is not practical. Perfect verification doesn't scale. AI might help with this continuing to go forward, but we know AI isn't perfect either. Practical approaches accept some level of unverified trust. The long-term security of open source ecosystems depends on sustainability. Various initiatives attempt to address this. GitHub sponsors open collective corporate sponsorship of projects, but many critical projects still lack adequate support. Organizations can take steps to manage open source supply chain risk. Maintain dependency inventories, tracking what you use as much as you can. Monitor dependencies for security issues and updates. Look for those AI tools that I mentioned. If they don't exist yet, they will. Review dependencies before adding them. Consider maintainer reputation, project activity, and code quality. Minimize dependencies where practical. Each dependency is a potential risk, so use only what you actually need. Implement automated dependency scanning and contribute to open source projects you depend on through funding, maintenance, or security review, improving economic security benefits. Despite all the different strategies that exist, zero risk is impossible when using open source dependencies. The benefits of open source: speed of development, community expertise, shared maintenance burden, come with inherent supply chain risks. Organizations have to accept some level of risk as the cost of efficiency and capability that dependencies provide. The goal can never really be eliminating risk no matter what you do, but managing it to acceptable levels while gaining benefits that make the risk worthwhile. In our next lesson, we'll talk about defending against supply chain attacks. You'll see what organizations can do to reduce supply chain risk, why perfect prevention is impossible, and how to build resilience to survive supply chain compromise.